on the changes that we can observe on a material when you increase its temperature. If you could recollect, in the lectures immediately following the introductory module, we introduced ourselves to different thermodynamic parameters that helped us to quantify or describe the changes in a material when you increase its temperature. So these parameters include internal energy, entropy, and Helmholtz free energy. So all these parameters, all the three parameters, helped us to describe what are changes that a material would exhibit when you increase its temperature. And these descriptions were rather general. They did not focus on any specific behavior of a material at high temperature. However, based on this understanding, we built upon it and then we arrived at understanding a rather macroscopic behavioral change at high temperature. In few lectures or two lectures before, we were able to understand how the thermal expansion occurs when you increase the temperature of the material, or what are the factors that govern the expansion of the material at high temperature. We saw that from the theoretical standpoint, we saw what are the factors that introduced this thermal expansion to the material, and we also tried to understand it from the atomistic point of view. So we have theoretical basis for this thermal expansion of material at high temperature, and also the atomistic behavior that leads to this thermal expansion. And based on our understanding of the thermal expansion, we built upon it and we introduced or we studied how the high temperature affects the mechanical behavior of the material, or rather how a material behaves when you impose it or when you impose a mechanical condition to it. So in the previous lecture, we saw how the Young's modulus of the material would change when you increase its temperature. Again, we saw the theoretical reasons on why the Young's modulus would change when you increase the temperature of the material. So in this lecture, we will build on that and we will move into the other aspect of the mechanical behavior of the materials, or rather how a material would respond when you impose a mechanical condition to it. Now, if you go back or if you look back at our fundamental understanding of how a material responds to an imposed mechanical condition, the easiest way to portray it, the easiest way to illustrate is by what we call as a stress strain curve. So this stress strain curve is something we are supposed to be familiar with. So in this stress strain curve, what we plot is ultimately how a material responds when you impose a mechanical condition or a load to it. So in this stress strain curve, typically it would comprise of a linear region and a non-linear region. So this stress strain curve can be characterized by or can be split into two regions depending on the nature of the relation between stress and strain. Now in the first region, in this region, the relation is rather linear, and in the second region, as you can see, it is a non-linear relation between the stress and strain. This linear relation is what we refer to as the elastic region, and in this region the material behaves elastically, and the slope of the curve in this region is referred to as the Young's modulus, or you can also arrive owing to its linearity. The Young's modulus is also the ratio of the stress and strain at a given moment. So this Young's modulus, it predominantly governs the elastic behavior of a material under an imposed stress or load. So if you impose a load, if I impose a load to a material within the elastic region, its behavior is predominantly governed by this Young's modulus. And now, by understanding how a Young's modulus changes with increase in temperature, what we have ultimately done is we have understood or we have attempted to describe how the elastic behavior of the material changes with increase in temperature, or rather we have just provided a fundamental pedestal on which to stand on to understand the or to describe the elastic behavior of the material at high temperatures, or when you increase the temperature of the materials. So now let's try to consider the other section of the stress strain curve. So far we have been focusing on the elastic behavior of the material or how a material would behave elastically, or how the elastic properties of the material would change, property of a material would change when you increase the temperature. Now in this lecture, let's build on that understanding, and let's move ahead and try to describe the influence of the temperature on the other region of the stress strain curve, the inelastic or the plastic region of the stress strain curve. So in this lecture, we will be focusing on how temperature changes the plastic behavior of the material. Now, depending on our understanding, particularly of how the atoms behave at high temperature, one can postulate something on what he or she could expect of the plastic behavior of the material. Now, in the previous lectures, we saw that with increase in the temperature, the atoms begin to vibrate, and the magnitude of vibration is proportional to the increase in temperature. And on top of it, we also saw that the internal energy of the material also increases with increase in temperature, and we were able to quantify it through the description of the internal energy. Now, this would mean that in addition to any energy that is applied or supplied to the atoms through the load, there is also an addition. That is also the thermal energy that can be used by the atoms to do whatever it wants. That means if you translate the plastic behavior of the material to the mobility of dislocation. So what I mean by that is, if you say that a material behaves dominantly in a plastic manner when the dislocations are able to move freely, then you could relate the atomic behavior of the material to the mobility of the dislocation. Meaning, if the atomic vibration helps the mobility of the dislocation, helps the movement of the dislocation, then it would mean that the plastic behavior of the material is enhanced. Let me repeat, when we say that, or when we postulate that with increase in the temperature, since there is an increase in the vibration of the atoms, or the magnitude of the vibrations of the atom, if this increase in the magnitude or vibrations of the atom, if this supports the mobility of the dislocation or the movement of the dislocation within the material, this would mean that this temperature or increase in temperature ultimately supports the plastic deformation of the material, or enhances the plastic deformation of the material. To put it simply, the increase in temperature enhances the plastic deformation of the material by facilitating or by enabling the easy mobility of the atoms. By enhancing the mobility of the atoms, the increase in temperatures or the increase or rise in temperature facilitates the plastic behavior of the atom, again through the mobility of the atom. So one can postulate something like this based on our fundamental understanding of what happens atomistically when you increase its temperature. So let us try to substantiate this claim from a theoretical standpoint. So in this lecture, this is exactly what we will be doing. So even though we are able to postulate something, even though we are able to make an educated guess on what to expect in the plastic behavior of a material when the temperature is rise through our understanding of atomic vibrations, in this lecture rather, we will try to provide a theoretical framework for this understanding or for this conjecture that we are proposing. We will try to we will try to see if the theoretical consideration supports this claim. For that, let us assume a dislocation, a rather simple edge dislocation with a Berger vector B. So this B is the magnitude of the Berger vector. So we will just confine ourselves to a simple edge dislocation with a Berger vector or the magnitude B. Now, there is a load being applied to a material, rather a one-dimensional material, and this load when it can be translated into the stress, and there is a component of this stress that is acting upon this dislocation. Let us consider, or let us say that this component of the stress as tau AP. So this is the component of the applied stress that is acting on the dislocation of Berger vector B. So what we now have is the component of the Berger vector, which is nothing but the dimension of the dislocation, and we have the component of the stress that is being acted upon the dislocation. Now if you could recollect, The load is nothing but the load. We refer to this load as this load is nothing but the force that is acting on a material. If you consider this unit, we would see the relation between the force and the load, that is its Newton, and this load again is nothing but, we can refer to this load as a force acting on this. Force acting on a material. So in this lecture, rather it is important to realize or relate load and energy, and this we have done in the previous lectures as well, and this will be helpful in understanding theoretically what changes we could expect when you raise the temperature of the material, particularly in the context of mobility of the dislocation. So if you want to understand the mobility or relate mobility of the dislocation to the increase in temperature, it is important to relate all the parameters that we study in terms of force and energy. This will give rather a standard platform for wherein we can play around with all the parameters that we have once we are able to distinguish this is a force and this is the energy. So let us look the load in terms of force, and this load per unit area is what we define as stress. And if you just want to express the load alone or the force alone, we would write it something like this. If you could recollect in your standard introductory book on mechanical behaviors, it would be written something like this, where the integral would correspond to the small area of the cross-sectional area of the material. Now if you do the same here, so what we have is a stress that is acting on a dislocation, and we have a Berger vector or a dimension that pertains to a dislocation. So the force that is acting upon a dislocation, similar to the load, the force that is acting upon the dislocation is proportional to the product of the stress and the dimension of the Berger vector. So I hope you are able to understand that and relate this to this, meaning the force acting on a dislocation is proportional to the stress acting on it, the component of the applied stress that is acting on it, and the product of its dimension, which is the Berger vector. Now it is important to note that the dislocation is not a point defect, rather a line defect. So in spite of our consideration that the system we are considering is a one-dimensional thing, it's one-dimensional in nature, we have to include the line dimension of the dislocation. Therefore, the force, the overall force that is acting on the dislocation is equal to the product of the component of stress, the dimension of the dislocation, and the length of the dislocation, particularly given that what we have is a line defect but not a point defect. So this is what the force acting on a dislocation is when you consider the stress that is acting on it. So we have an applied load, we have based on the applied load, we have a stress to which the material is exposed to, and a component of the stress, it is acting on a dislocation with a Berger vector B, and we want to know what is ultimately the force that is acting on the Berger vector, and we have arrived at this relation based on our basic fundamental understanding of the stress strain or definition of the load, and based on the fundamental understanding of the definition of the load, which is nothing but the force, we were able to arrive at this expression for the force that is acting on the dislocation, which is nothing but the product of the applied stress and the magnitude of the Berger vector along with the dimension of the line defect L. So now let us assume that there is rather an obstacle that is preventing the dislocation to move from point A to point B. So point A to point B, there is an obstacle that is preventing to move a dislocation, this dislocation. Now this obstacle, rather this is point A and this is point B. So this obstacle rather it presents itself with a negative or a resistive force which can be graphically expressed in this form. So there is a resistive force that the obstacle that it provides or it offers or it impedes the movement of a dislocation through a resistive force of say R. Let's just call this as R maybe. So we have a resistive force that prevents the mobility of the dislocation from point A to point B, and graphically we have represented this in the resistive force in this manner. For now, the dislocation to move from point A to point B, it has to overcome this resistive force, and let's just assume this to be X. So it has to overcome this resistive force. So what we have seen is we have now have an understanding of the force acting on the dislocation, and now let us try to define, or let us try to provide an understanding of this resistive force. So this resistive force ROB, it changes within these points A and B. It changes. It is not linear in nature. Now suppose one has to define the energy that needs to be overcome. So we have plotted, all we have plotted is a resistive force here, and we call that as ROB, and one wants to talk in terms of energy, not in terms of force. We have to go back to our the fundamental understanding of how we related force and the energy when we are talking about the interatomic potential. If you could recollect, we were able to arrive at a plot for the interatomic forces by considering the derivative of the interatomic potentials. We were talking about how in the previous lecture we wanted to arrive at a relation for the Young's modulus, and we wanted for this derivation we wanted to have a plot for force acting on an atom. So this plot we arrived at by considering the interatomic potential and particularly considering the derivative of this interatomic potential, and we were able to show that the force acting on an atom is nothing but the slope of the potential energy between the atoms, or the first derivative of the potential energy between the atoms. So this is the way we related force to the internal energy or the potential energy. Now what we have here is we have how a resistive force, how the resistive force varies from point A to B, and what we need to arrive at is what is the energy of this obstacle. Or if we understand the energy of this obstacle, it will be easy for us then to arrive at an expression that will show us what is the energy required for the dislocation to overcome this obstacle. So for that, let us try to arrive at, or let us try to postulate or calculate what is the energy of the obstacle, or let's try to calculate the obstacle energy for an obstacle of this which imposes a resistive force in this pattern. So if this is the force which can be related to this expression, then it would mean that the obstacle energy, or the derivative of the obstacle energy with respect to S, is the force that we are talking about here. So like I said, we have related force to energy by considering the derivative of the energy. This we have done in the previous lecture. When we translate that to the present condition of the force that the obstacle imposes on, or the obstacle presents itself, then by relating this force to the obstacle energy, we will be able to quantify the obstacle energy. Now the obstacle energy DEOB can be written as the product of the force, that is resistive force that is offered by the obstacle, and the distance separating the point A and B. Now when you consider the integral of it, the overall energy of the obstacle will be something like E to B, or so this is what the overall energy of the obstacle, which offers a resistive force of ROB, or the obstacle resistive force, this over a distance of dx. So we will be able to relate or calculate the obstacle energy based on this relation here. So the fundamental basis for this relation is the expression here, which we have seen in the previous lecture, and now we have an expression for calculating the obstacle energy that needs to be overcome by the dislocation in order for it to be to cross this particular obstacle. So when the dislocation is able to overcome this obstacle energy, it will be able to move freely. So let us begin by considering how one can represent this obstacle energy. So what we have seen is that we have an obstacle that provides a resistive force of ROB between points A and B in the x-axis, and we saw that this is how the force varied between A and B, and when we calculated based on our understanding of the relation between force and energy, when we calculated the energy of this obstacle, we had this relation, we arrived at this relation 1. And if you try to visualize this relation, it is nothing but the area under the curve of force ROB within the points A and B. So this is what the dislocation needs to overcome. The dislocation, it needs to overcome this energy in order to move from point A to B. Only when the dislocation is able to overcome this obstacle energy, one can expect its movement from point A to B. Now let us go back to our description of the force that is acting on the dislocation. We have expressed it in this way. So now similarly we can arrive at an expression for the energy of the dislocation. So if you talks about the energy of the dislocation, all that we need is the integral of the component of the applied stress that is acting on the dislocation, the Berger vector B, the dimension of the dislocation, and we have to consider the dx from point B to A. So this is one way to describe the energy that the dislocation possesses because of the load that is that the dislocation experiences. Now the dislocation experiences a particular load, and because of this load we were able to calculate the force that is acting on the dislocation, and based on this force or translating this force to energy, we have arrived at this expression. So we have arrived at an expression, or we were able to relate the force experienced by the dislocation or translate the force experienced by the dislocation into the energy of the dislocation. Now there are two cases that are possible. Now if you consider a case like this, so this would mean that this dislocation or we can assume that this dislocation is able to, or the energy of the dislocation is equivalent to that of the energy of the obstacle. So let us assume a case 1 like that, wherein we have that the energy of the dislocation is equal to the energy of the obstacle. So that would mean that the energy of the dislocation in itself, or the energy that comes to the dislocation from the mechanical loading condition itself, quite possible it itself provides the sufficient energy to overcome the obstacle. So that means the load is sufficient enough to overcome the obstacle. So we don't need any support from the temperature or the atomic vibration in order to help the dislocation to move from point A to B. So everything that is needed to overcome the dislocation energy, if to be more clearer, if we assume that the energy of the dislocation is greater than or equal to the energy of the obstacle, in this case, just by the virtue of the load that is imposed on the material, the dislocation can move from point A to B and overcome the obstacle in between these points just by the virtue of the imposed loading. Now let us consider a case 2, wherein we define or we describe, let us consider the case, let me make it clear, let us consider a case 2 wherein we describe the energy of the dislocation as something like this. So instead of taking the integral, let us define the energy of the dislocation something like that, like fairly simple, like this, B minus A. So what we mean by this description of the energy of the dislocation is, let us plot it graphically. So what I mean by that is, so what we have is the resistive force that is offered by an obstacle between point A and point B. Now within the same point A and B, the energy of the dislocation is expressed by this term. So this would come here. So this much of the energy is provided by the dislocation. So if you want me to separate it, so this much of the energy is provided by the dislocation. So that is what we mean by this expression here. So the energy of the dislocation, it becomes the part of the overall energy or the obstacle energy that needs to be overcome in order for the dislocation to move from point A to B. So when you consider such a case wherein the energy of the dislocation is expressed by this relation, it means the part of the obstacle energy is able to, the mechanical condition or the imposed load is able to provide the part of the energy of the overall obstacle. So we have an obstacle energy, that is the overall area under the curve. Even though the imposed load is not able to provide the overall energy or the energy that is equivalent to the obstacle energy, as in case 1, we have now considered a case 2 wherein the load is able to provide a part of the obstacle energy. However, since this energy, which is purely because of the mechanical condition, is less than the energy of the obstacle, since we have not yet, there is the energy, there is still this much amount of energy that is left for the dislocation to overcome. The current condition is, when you consider just the contribution of the mechanical load alone, the energy of the dislocation is less than the energy of the obstacle. So that means, as in this condition below, the dislocation will not be able to move from point A to point B. So for the dislocation to move, the amount of energy that needs to be supplied to the dislocation is nothing but, can be expressed as something like this. So now when we are able to supply, in this condition, when we are able, in this case, when we are able to supply this amount of energy, that is delta E, then the dislocations will be able to move from point A to point B, thereby making sure the material behaves plastically even though there is an obstacle that imposes a definite resistance. So the easy or the mobility of the dislocation in this case too is only possible when you supply an additional energy of delta E. Now we have seen that with increase in the temperature, the internal energy of the system increases, the internal energy of the atoms increases. So if you have a system of n components, and the internal energy of the components will be the summation of this n components, and in component I mean is the components can be atom, molecules or anything. So internal energy of the overall system is the combination of the internal energy of the individual components that comprise the system, and the internal energy of the individual components that comprise the system, we calculated that in our previous lecture. We saw that it is the summation of the potential energy at its equilibrium position because of the interaction between the atom. It has this potential energy because of this equilibrium position, and a vibrational potential energy that can be expressed in this manner. And similar terms you will be having for y square and z square. This is the vibrational potential energy, and if you could recollect, this p term is the double derivative of the potential energy. And we have this, in addition to the vibrational potential energy, we have the kinetic energy of the atoms. So when you increase the temperature, what we are essentially doing is, we are essentially increasing the energy of the atoms which ultimately constitute the material, in our case which ultimately constitute the dislocation. So what we saw is, for the dislocation to move, in our case we need an additional energy in order to overcome the obstacle, and we have seen with increase in temperature we are providing some energy to the atoms that constitute the dislocation, and this we can make some assumption. And if we just take this part alone, that is the vibrational potential energy and the kinetic energy, which comes only because of the increase in temperature. When you consider an absolute temp 0 or 0 Kelvin, these parts will be, or these contributions will be also 0, and these comes only because of the increase in temperature. So these are referred to as the thermal energy contributions or the thermal energy. Now when we consider the thermal energy, we made an approximation about the harmonic vibration. We introduced the theory of, or the assumption of, equipartition, and we were able to show, or we were able to arrive at the result that the individual components of these vibration potential and the kinetic energies in individual direction, they are equal, and they amount to, on an average, they amount to this product, which is half kappa T. Kappa is the Boltzmann constant and 3 is the temperature. And now we have 6 components, 2 pertaining to each directions. So we have 6 components, 2 pertaining to each directions, because we have a vibration potential energy and a kinetic energy in the x-axis, and similarly 2 components in y-axis, similarly 2 components in the z-axis. So we had the overall change or the contribution of the thermal energy as the product of 6 into half kappa T. Now in our case, what we have is we have been considering just a one-dimensional system and change in the longitudinal length alone. So that would mean that we are not considering the contribution from the y and z axis. So it would ultimately lead to if the 6, the degree of freedom 6 would reduce to 2, and the change in the internal energy would correspond to the same, or the thermal energy would correspond to the same, and ultimately the increase in the energy due to a particular temperature due from the absolute 0, the energy of an atom at a temperature T can be quantified as this. Please note that what we arrived at this relation by considering the vibrational potential and the kinetic energy, we were able to classify them as the thermal energy, and we were able to show for our present consideration of one dimension, the internal or the energy of the atoms can be quantified as the product of Boltzmann's constant and temperature. So this we got rid of the prefactor 3 because and since we consider a one-dimensional system, we have to ignore the contribution from the y and z axis. So ultimately what we have is this relation. Now what we want to know is if this energy, which is nothing but or which the dislocation needs to have in order to overcome the obstacle, is being supplied by this thermal energy. So we have an obstacle energy that needs to be overcome by the dislocation, and we have a dislocation energy that comes from the stress that is applied to the dislocation, and we want to see if the thermal energy is able to provide this additional force or this additional energy for the dislocation to overcome the obstacle. Now if we have a condition like this, if we define the energy of the atoms that constitute the dislocation in this manner, the probability that this energy is able to overcome or provide energy of this quantity, the probability that at this temperature the thermal energy would be equal to delta E. Let me repeat, the probability at which the thermal energy kappa T is able to provide or able to add to this or able to provide an energy of this magnitude is expressed by this relation. The probability that the thermal energy kappa T is able to provide the additional energy of this form is expressed as minus kappa T. So now what we have is we have a probability relation that shows that when you have a thermal energy of kappa T, the probability of this kappa T giving you this additional energy in order for the dislocation to overcome the obstacle is of this form. And now when the temperature is higher, this probability becomes higher, and that would mean that the additional energy that is provided to the dislocation will also be higher. So ultimately when your summation of the dislocation energy plus the thermal energy is greater than the obstacle energy, your dislocation will be able to overcome the obstacle and move from point A to point B. So what we have ultimately arrived at is, we have seen that there are two ways that a dislocation can overcome the obstacle. When the applied load provides sufficient energy for it to overcome the obstacle energy, it can propagate from point A to point B easily. Now if the applied load is insufficient to overcome or to render an energy to overcome the obstacle energy, that would mean that the obstacle then impedes the mobility of the dislocation, thereby restricting the plasticity of the material. However, when you increase the temperature and when the thermal energy increases, the probability of the thermal energy catering to or adding to the dislocation energy and providing an energy that is greater than the obstacle energy increases, meaning with increase in temperature, the thermal energy would be sufficient enough to overcome or the combination of the dislocation and the thermal energy would be sufficient enough to overcome the obstacle energy. That means the dislocation can move from point A to point B easily. That means that the material will behave in a more plastic manner when you compare it to the ambient temperature. So what thermal energy ultimately does is it adds to the dislocation energy. When it adds to the dislocation energy to a degree that it is able to overcome any obstacle energy or any obstacle energy of any form, then it would mean that it ultimately contributes to the plasticity of the material. So when we say that with increase in temperature the plasticity of the material increases, then what we are ultimately stating is that the thermal energy that increases with increase in temperature, it enhances or it adds to the dislocation energy, and this combination of dislocation energy and thermal energy, they both combine, and this combination of energy helps the dislocation to overcome any obstacle, thereby ultimately causing plastic behavior or thereby ultimately enhancing the plastic behavior of the material. So the temperature through the thermal energy of the atoms enhances or it adds to the dislocation energy and helps the dislocation to cross over the obstacle or cross over any resistance force that the obstacle presents, and thereby facilitating the plastic behavior of the material. So this is one way how a temperature enhances the plasticity of the material. The first way is by enhancing or adding to the dislocation energy through the thermal energy. The increase in temperature adds the thermal energy to the system, and this thermal energy combines with the dislocation energy that comes from the load, and in combination of thermal and dislocation energy ultimately makes the dislocation to overcome the obstacle. So this is one way that the increase in temperature can cause or can facilitate the plastic deformation of the material. There is another way that is also possible. Now let us go back to our graphical representation of the resistive force that is offered by the obstacle and between the points A and B. So this is the resistive force that is imposed or that the obstacle presents between point A and point B in the one-dimensional direction x. Now if you plot this obstacle force like this obstacle force, it is often confined to a particular slip system. When we talk about a dislocation or the movement of a dislocation, this is confined to a particular slip system, and we talk about an obstacle during this movement, it ultimately or implicitly means that we are talking about an obstacle that is confined to a slip system. If there is another obstacle that pertains to another slip system, the resistive force offered by it will vary. So let us now consider, so what this plot ultimately means is, or what this plot implicitly means is that we are talking about a particular dislocation moving in a particular slip system, and the obstacle is also confined to that slip system. Now we have seen that the dislocation needs to overcome this amount of obstacle energy in order to move from point A to point B. And now we have, in the case 2, we have seen that even though your dislocation or your stress is able to give only this amount of energy, when your stress is able to give only this amount of energy, it is possible that due to the increase in temperature, the thermal energy would provide an additional energy of this much, which in combination with the dislocation energy would enable the dislocation to move from point A to point B. So this is what we saw in the previous discussion. So we have our dislocation energy from the load, and we have the thermal energy from the temperature. The combination of these two help the dislocation to move from point A to point B. Now let us try to plot how this, let us consider a case wherein we have two slip systems, and each slip system they present their own obstacle or their own resistance. So let us plot two slip systems and the resistance offered by this slip system. So in the slip system 1, the resistive force that is offered by the slip system 1 is defined by this 1. So this is between point A and B, and there is another resistive force that is imposed by another slip system, that is 2, for the same point between A and B. So now, so this is the resistive force and this is along the mobility direction, that is x. So what we now have is two slip systems. They offer two different resistive force for a movement in from point A to B. So of course this direction might vary depending on the slip system, but let us just normalize the direction and present it in the in a singular axis of this plot. Let's present let's get rid of the direction. We can normalize it and we can present it in the single x-axis, and we have done it. So what we are talking largely about is we are talking in a one-dimensional direction for two different slip systems, and how the resistive force for the two slip systems vary. So what we have is, we have two slip system 1 and 2. They both offer two different resistance for the mobility of the dislocation. When your combination of the dislocation energy, let's just call it as 1, and the thermal energy. So when you have a combination of dislocation and thermal energy at temperature, or rather at temperature T1. So at temperature T1, what you have is a combination of dislocation and thermal energy, which is given by this here. So at temperature T1, we have a combination of dislocation energy and thermal energy. So since these combinations are greater than that of obstacle energy at 1, or the obstacle energy at T1 for the slip system at temperature T1, so this would mean that we have seen this is the overall energy, or the dislocation energy that comes from this is the overall energy, the summation of the dislocation energy and the thermal energy, and since it is greater than the obstacle energy at the slip system 1, since the combination of dislocation energy, which is marked by red here, the combination of the dislocation energy and the thermal energy, which is demarcated by blue here, since the combination of these dislocation and thermal energy at temperature 2 is greater than the obstacle energy at slip 1, the dislocation will choose a path, or will choose slip system 1 to move from point A to B. The combination of dislocation energy and thermal energy at temperature 1 is greater than the obstacle energy at in slip system 1. So therefore, when the dislocation wants to move from point A to point B, it chooses the slip system 1. Now, I hope I have made this point clear. So please allow me to reiterate. So we have two slip system 1 and 2, and for a temperature T1, we have dislocation energy, which is dependent on the imposed load, and the thermal energy, which is dependent on the temperature. Now the combination of these dislocation and the thermal energy is greater than the obstacle energy at the slip system 1. Therefore, at T1, what happens is that when the dislocation wants to move from point A to point B, it chooses the slip system 1 to move, because the combination of both dislocation energy and the thermal energy is greater than the obstacle energy at slip system 1. Therefore, at T1, the dislocation at T1, the dislocation chooses the slip system 1. Now let us consider a case T2. So let me move back to black here. So let us consider a temperature T2, an increase in temperature, that is T2 is greater than T1. So let us consider the resistance offered by the obstacle at the two different slip system as we considered in the previous case. So we have two resistance that is offered by the slip system like in the previous case. Now since the temperature has increased, that means that we have now a new thermal energy that is greater than the thermal energy at the new thermal energy 2 that is greater than the original thermal energy 1. Our dislocation energy, which depends on the loading, would remain unchanged, so that will remain 1. Now this resistance is offered by the slip system 2 and this resistance is offered by the slip system 1, and this is the resistive force that is offered by the resistive force that is offered by the obstacles at different slip system, and this is the direction or the one-dimensional scalar value. So now we want our dislocations to move from point A to B, and we have repriced the temperature of the system. Now the combination of the dislocation energy and the new thermal energy can be expressed, or in this at temperature T2 is denoted by this manner. So like the initial case, since the load hasn't changed, the dislocation energy, which depends on the applied load, will not change. So this remains the same. So this is the dislocation energy that comes from the loading aspect, or that comes from the mechanical contribution. Now what has changed is we have increased the temperature. That would mean that the thermal energy has changed. Now the new thermal energy is something like this. It has increased with proportionally with the temperature, and it is something like this. Now what we ultimately have is the combination of the new thermal energy, that is ETH2, and the dislocation energy is greater than the obstacle energy at the slip system 2. Now as we increase the temperature, the thermal energy is sufficient enough to overcome the obstacle at the slip system 2. So what now happens is, at temperature T2, the dislocation can prefer both slip system 1 and slip system 2 to migrate. So let me repeat, by increasing the temperature, we have provided sufficient thermal energy for the dislocation to overcome not only the obstacle in slip system 1 but also the obstacle in slip system 2. In the lower temperature 1, the thermal energy was only sufficient to overcome, or the combination of thermal energy and the dislocation energy was only sufficient to overcome the obstacle in slip system 1. But now that we have increased the temperature sufficiently, the thermal energy is also sufficient enough to overcome the obstacle in slip system 2 in combination with the dislocation energy. Now what we have ultimately done is, we have enabled the dislocation to move from point A to B through two slip system, that is 1 and 2 is now available for the dislocation to choose, or it can move, or it can choose both, or it can, the energy is sufficient for the dislocation to either move from point A to B through the slip system 2 or through the slip system 1. So ultimately, to put in general terms, what we have done is, we have activated new slip systems. So now when you have, instead of one slip system but rather two slip system which enables your dislocation to move, that would mean that ultimately you are also enhancing your plasticity. So what we have so far done is, we have enhanced the plasticity in two ways. One is, we have provided an additional thermal energy for the dislocation to overcome the obstacles. We have provided, by increasing the temperature, we have provided additional thermal energy for the dislocation to overcome the obstacle and to move freely. So we have facilitated the easy movement of the dislocations through the supply of the thermal energy. Now what we have also done is, we have also enabled or activated new slip systems by virtue of this thermal energy. So at high temperature, the thermal energy becomes so high that it also activates, or this also provides new way for the dislocations to move, thereby also ultimately increasing the plasticity of the material. So the temperature, the influence of temperature on the dislocation, so far we have seen on the movement of the dislocation, thereby the plasticity, is so far in two manner. That is, one, by directly providing the thermal energy, thereby in combination with the dislocation energy facilitates the easy movement of the dislocation, thereby ultimately increasing the plastic behavior of the atoms or the plastic behavior of the materials. The other way, the high temperature helps or enhances the plastic behavior of the material is by activating new slip system or increasing the thermal energy in such a manner that the obstacles or the probability or the propagation of the dislocation in the new slip system is also possible. So by these two possibilities or by these two fashions, the increase in temperature facilitates the mobility of the dislocation or the movement of the dislocation. So far we have seen there are two ways that increase in temperature would affect the plasticity of the material. So one is just by providing an additional thermal energy, as we have seen here, and this additional thermal energy in combination to the dislocation energy that comes from the imposed stress would enable the dislocation to move rather freely or would enhance the dislocation of or the moment of the dislocation, thereby ultimately enhancing the plasticity of the material. The other way in which the temperature would facilitate or enhance the plasticity of a material is by activating new slip system. We saw that at high temperature, with sufficient increase in the temperature, the thermal energy sufficiently increases to encompass the or to overcome the obstacle energies of other slip system, thereby facilitating the movement of the dislocation in those slip systems as well. So by increasing the temperature, we also activate additional slip systems and thereby facilitating or enhancing the plastic behavior of the material. Now allow me to provide an additional way in which, or present an additional way, the high temperature enhances the plastic behavior of the material before I wind this lecture up. So let us consider just one way or one additional way on how the high temperature enhances the plastic behavior of the materials. Now, with increase in the temperature, in addition to the increase in the thermal energy of the atoms and also the increase in the magnitude of the vibrations of the atom, the vibration or the number of point dislocation also increases. Particularly with increase in the temperature of a material, the number of vacancies associated with the material also increases. Now these vacancies, when they increase, they ultimately reduce the obstacle potential or obstacle energy in a slip system. So when an obstacle energy is reduced at a given temperature for a given combination of thermal and dislocation energy, it means that the combination of thermal and dislocation energy allows the dislocation to move easily in that slip system. So with increase in the amount of vacancies, with increase in the number of vacancies, the dislocation can move rather freely. Thus the increase in temperature, which facilitates this increase in vacancies, ultimately contribute to the enhancement of the plastic behavior of materials at high temperature. Now let us see how, in what manner this vacancy or the number of vacancies increases with the temperature. So earlier here we have seen that for a thermal energy of kappa T, the probability to overcome it is given by this expression. So this expression can be translated to arrive at the equilibrium composition of the vacancies. So here this thermal energy, based on this thermal energy, the probability to overcome this difference in energy was calculated. So this similar expression can be used to calculate the equilibrium composition of the vacancies. Now the equilibrium composition of the vacancies is expressed in this manner. So this is equilibrium composition of the vacancies is equal to exponential term or rather kappa T. Now kappa T comes from the thermal energy at a temperature T, and E vac is the energy required for the formation of vacancies. So we have an expression that relates the amount of vacancies in a given system at a temperature T through the energy required for the formation of vacancies. So this according to this relation, as the temperature increases, the number of vacancies also increases. So ultimately, as the number of vacancies increases, the obstacle energy subsequently decreases, thereby facilitating easy mobility of the or easy movement of the dislocation, which translates to the plastic behavior of the materials. So what we have seen in this lecture is, we have seen three ways high temperature contributes to the plastic behavior of the atoms or the plastic behavior of a material. So the first way is, with increase in the temperature, we increase or we provide a thermal energy to the system. This thermal energy, in combination to the dislocation energy that comes from the imposed or the load condition or the imposed mechanical condition, is able to overcome any obstacle energy pertaining to a slip system, and this will cause a easy movement of the dislocation, thereby contributing to the plasticity of the material. Additionally, when the thermal energy is sufficiently large enough, it is able to activate slip systems by overcoming the obstacle in those slip systems. So we have different slip systems and they offer different obstacle force or obstacle resistance. When the thermal energy is sufficiently high to overcome this obstacle resistance, that would mean that the dislocation are now possible to take any of these slip systems, and now we have increased slip system for the dislocations to propagate. That means that the mechanical or the plastic behavior of the material is enhanced. So by activating new slip systems, the plastic behavior is enhanced at high temperature. And finally, we see that by increasing point defects, there is a possibility of increasing the plastic behavior of the material by reducing the obstacle energy. So by reducing the obstacle energy through the point defects, it is possible for the dislocation to propagate easily, and by virtue of it, the plastic behavior is also enhanced. So what we have seen in this lecture is quite lengthy lecture, I agree, and I can say. So what we have seen in this lecture is, we were able to provide or substantiate our claim that with increase in temperature, the plastic behavior of the material is enhanced or increased. So this we were able to do it from a theoretical standpoint by considering the mobility or the movement of the dislocations. So we saw the movement of the dislocation is enhanced by the thermal energy. It is also enhanced by the creation of the new slip system, and it also enhanced by the reduction in the obstacle energy through the formation of the point defects. So please listen to this lecture. Like I say, I consider that it's a pretty lengthy one. So please listen to this lecture at your own pace. If you want, you can run this lecture at a faster pace, wherein the things that you are already acquainted with are dealt. So you can run those sections of the lecture at a faster pace, and you can choose the normal phase for the other new section or the sections wherein the new aspects are covered. So please listen to this at your own pace. Since this being a lengthy lecture, I would give sufficient amount of time for you to listen to it, and of course you can approach me if you have any questions, and try to get an understanding or get a theoretical substantiation for why the material behaves in a more plastic manner when you increase its temperature. So we have provided several reasons. Just try to get a theoretical understanding of why such enhanced plastic behavior is observed at high temperature. So let's see ourselves in the next lecture. Please let me know if you have any questions. Goodbye.